Good evening. I'm Stewart Brand from the Long Now Foundation, and we're doing a serious long now tonight. Here we have a mathematical physicist who's doing something that is really at the core of what the Long Now Foundation has been trying to get at. And I think I first saw a version of it back when I was a skydiver in the 1960s. And the thing about skydiving is when you're in the plane, somebody jumps out, they're right there in the wind, and they get real small. And when it's you jumping out, you're out there in the wind, and you push the plane away, and it gets real small. And that's pretty much how we live in time. But one time, there was two planes, two sticks of jumpers, and I was in one plane watching the guys jump out of the other plane. Guy gets out on the strut, lets go, and plummets! I'd never seen skydiving from the side before. It was horrifying. Shortly after that, I had a malfunction, which tried to kill me and failed. But the combination of those two events made me stop skydiving, and I'm here today. I learned. We seldom do that with time. And in a sense, what John Baez is here to do tonight is look at time not from within it, where we're telescoping out in one direction, telescoping out in the other direction, but looking at it from the side and seeing what kind of patterns emerge there and how you can get a handle on things from that perspective, or you might do something about them if you don't happen to like them. Please welcome John Baez.
Thanks very much. It's great to be here. Stewart Brand and Kevin Kelly have been heroes of mine, and so it's nice to be able to talk to them, even if I'm standing up here, and the rest of you, of course. So I'm a mathematical physicist, so I usually think about things that are either bigger than that or smaller than you can see, but I thought I'd do something a little bit more human in scale and talk about history and the weather. And so right now we're in a very strange moment in history. Things are changing mighty fast these days. As you, I'm sure, have heard, there's this thing called Moore's Law, talking about how computers are working ever faster, but really that's just a tiny bit of a much bigger story, which you can see maybe pretty well on this graph here. A lot has been happening in the last couple hundred years, and it blinds us to the overall scope of time. So this is a graph of population starting from approximately around the end of the last ice age till now, and you'll see that it ramped up in retrospect fairly slowly until the second agricultural revolution, when modern machines started getting used for agriculture, and then it shot up. And so if you were to naively extrapolate a trend from this curve, you'd conclude that in about 30 years from now, the population of the world will become infinite, and that's the singularity, when the Earth collapses into a black hole under the weight of all the people. Well, we can tell that that's probably not really going to happen. It would be against the laws of physics. So it shows you have to be a little careful when you're extrapolating curves. And luckily, if you were able to zoom in on the top of this curve a lot more finely than we have accuracy here, you'd see to your relief that it's beginning to slope down slightly. I mean, not slope down, but slope up less fast. So there's a little hope for us. But the problem I want to talk about is not the what's going to be the most likely continuation of this curve. It just has to do with trying to understand time on a large scale. Trying to understand history when we're standing right here is a lot like trying to understand geography when you're hanging onto a cliff. You think of geography as vertical, but most of it's not, but you just can't see it, and you're scared stiff. So I want to zoom out a bit and see what history is like on a slightly larger scale. And of course, history is incredibly complicated, so I thought I'd focus on something that we all know something about, namely the weather. So the weather is a hot topic these days because all this rapid expansion in human population and other things like technology goes along with burning stuff. We basically fuel our existence these days by burning carbon. And just like the population curve shoots up all of a sudden in the last 2 centuries or so, same for the CO2, carbon dioxide emissions, mainly from burning oil, coal, and gas, as you can see here. But you can see how remarkably it's shot up from what looks like nothing to quite a lot. And of course, that has an effect on things. That has an effect on the weather. It has an effect on the air, first of all. So here's a graph over the last 40 years, I guess, of how much carbon dioxide there is in the air. The red curve is the real thing, measured in Hawaii. The blue curve is sort of an averaged out version of that. And you can see it's been going up. Of course, you can make any graph look scary if you plot it correctly, so you should always be careful and look at the bottom of the graph here. So it's not starting from 0. Don't blame me for making this graph. I would like to start things at 0 and make it look a little less scary. But still, it's pretty scary because it's gone from 300 parts per million to about 400 parts per million in the last 40 years. So that means there's about a 30% increase in the amount of carbon dioxide in the air over just the last 40 years. And as we'll see, 40 years is a pathetically small amount of time if you measure it in geological time scales. So for the Earth's atmosphere to change so drastically in such a short time is really an unprecedented thing, or almost unprecedented thing. So that's what I want to talk about. Of course, you've heard a lot about global warming, but unfortunately, usually what you hear about it only focuses on a tiny sliver of history, which doesn't really give you enough of a view of it to really see what its impact or what its significance is. Just in case you're curious, the wiggly red curve there has to do with the fact that there's an annual cycle in how much carbon dioxide there is in the air. Most of the plants live in the northern hemisphere, and so when it's summer in the northern hemisphere, they eat up carbon dioxide, and the carbon dioxide goes down, and then during the winter it goes back up. And all this is very beautifully visible in that graph. But anyway, the increase in carbon dioxide goes along with increase in temperature because infrared radiation leaving the Earth, trying to get back out to space, gets absorbed by carbon dioxide. And so we've been seeing an increase in temperature ever since the Industrial Revolution, roughly 1860 here in this graph. And you can see it's a very complicated wiggly curve. The blue curve is the real thing. The red curve is averaged out, so you get more of a sense of it. But you can see anyway that its temperature averaged over the whole world has gone up 0.8 of a degree centigrade, or I guess that's something like 1.5 degrees Fahrenheit, over the last, I guess, roughly 150 years. And that's a big deal. But it doesn't sound like a big deal when you first hear about it. If someone says, well, the temperature went up 1.5 degrees, you say, well, that's no big deal. But the reason why you can't tell even whether it is a big deal or not is because we're looking on such a short time scale. So to see what's really going on, we have to zoom out to a larger time scale to see if this is just some random wiggle that'll go away or what. So let's zoom out a little bit here. So instead of just looking at the last 150 years, let's look at the last 15,000 years or so and see what the temperature has been doing. This is actually the temperature in Greenland. Temperatures up in places like Greenland are much more variable than near the equator. So this shows some drastic variations. They'd be less if you measured it near the equator. But anyway, you can get the picture pretty clearly. This is all from digging a 2-mile deep ice core in the glaciers in Greenland that let you go back and see yearly variations in various things like the isotope concentration in the ice, and get a sense of the temperature over that time period. And you'll see the main thing here is that there had been an ice age till around 12,000 years ago, and then it warmed up, and it's been surprisingly even in temperature ever since. So we've lived, meaning we, the we of recorded human history, we've lived in a sort of false sense of security in terms of thinking that the climate's more or less constant, when in fact, if you go back just a little bit further, you see there are much more jagged variations in temperature. So that rise in temperature that I showed you on the last slide is just a tiny little thing right there. And so if you look at that, then you might say, well, gee, what are people worried about global warming? Maybe we should be worried about the next ice age instead. And that's sort of true, but we'll see. There are different views you can take on this. I just want to talk about a couple wiggles on this curve. So first I'll talk about a tiny little wiggle called the Little Ice Age, which is a little dent right next to that bump there. But because it's fairly recent, it has its own name, whereas most of these wiggles, of course, don't have any name. And then I want to talk about a more interesting, well, not more interesting, but more substantial wiggle, which is called the Younger Dryas episode. So right as the last ice age was ending, it was warming up, then the temperature plunged around 13,000 years ago, and that's an interesting story in itself. So let's just take a look at those, and we'll get a sense of what kind of things the climate can do. So the Little Ice Age was from around 1550 to 1850, and the temperatures in Europe dropped about 1 degree centigrade, so it's about 1.5 degrees or so Fahrenheit. Near the equator, apparently it was a bigger deal. It was about a 2-degree change. But it was noticed by people at the time just due to the fact that winters were colder than they had been. And people have done studies of paintings, the history of paintings, and they find more of these kind of scenes during that stretch of time. There's a lot of controversy over how big a deal that fluctuation was, that is, how much it actually mattered. In particular, it's an interesting question because it ended right when the Industrial Revolution started, around 1850. So we may have ended the Little Ice Age by pumping lots of carbon dioxide out into the air. So maybe it wouldn't have been so little if we hadn't done something about it, regardless of whether we wanted to, we did. So that's a little wiggle. It makes people be able to walk around on the ice in the winter in the Netherlands, whereas now they can't. But a bigger wiggle was this Younger Dryas episode, which began about 12,900 years ago. So that was a shocking event. In only 20 years, the temperature in Europe dropped by 7 degrees centigrade on average. And that lasted for 1,000 years, and then suddenly in another 20 years it ended. So what's 7 degrees mean? Well, 7 degrees means that France and Germany became tundra, and Scotland had glaciers on it. And you can see, if you can read these not too readable letters, that the climate was really drastically different in Europe than it is now. So our ancestors, who were just beginning to practice agriculture at around that time, had to put up with 1,000 years of cold, really, really cold weather. And luckily, I guess, it didn't kill us off. We just made do. And then, all of a sudden, in another 20 years, it popped right back up to what we know now. So this is an interesting question. Why did that happen? No one really knows why it happened. There's a theory which is interesting, which goes like this. So you've all heard that the reason why Europe is warmer than a comparable place up here in Canada is because the Gulf Stream carries heat from the southern latitudes up past the coast of Europe. In fact, I just heard recently that that's somewhat controversial among scientists these days. They've really been trying to understand exactly what's going on, and it's not as clear as you might think. But according to this theory, which I'm telling you, which was a popular theory for a while, the key to understanding the younger Dryas was this current flow, which keeps Europe warm. And an interesting thing happened, which is that towards the end of the last ice age, Canada was covered with glaciers. And so the edge of those glaciers, there was a lot of glacial runoff. Melted ice formed lakes. And there was a huge lake called Lake Agassiz, which is that light blue thing there, which is by now shrunk down to smaller lakes like Lake Winnipeg, so in Manitoba there. But this lake was huge, and it was blocked from flowing to the sea by ice. It was blocked by lots of ice. But it's known that several times it actually managed to erode its way through that ice, and there were huge floods where the lake emptied out through the St. Lawrence Seaway and up into the north, poured out into the North Atlantic. This is known through studies of sediment at the bottom of the North Atlantic. There are actually lots of periods when this this lake would bust free and carry lots of rocks, and there'd be layers of sediment. But it's possible that the fresh water from that lake was enough to screw up the Gulf Stream, and ironically, the melting led Europe to get a lot colder because the Gulf Stream was blocked. So in fact, if I had given this talk about 6 months ago, I would have just said, this is the truth, this is how it works. But recently, people have started doubting that for various reasons, both because they don't think the Gulf Stream is quite so significant, and also because they've done a lot of ice cores in mountains in the tropics. There are some mountains like Mount Kilimanjaro and other less famous ones that have ice even though they're in the tropics, and they discovered that the younger Dryas episode was just as pronounced there, and maybe even came before its appearance in Northern Europe, which would mean that there was some other cause, perhaps, for why Europe got frozen. So that's just, I think, a mystery at this point. It's a pretty important mystery, though, because suppose it was fresh water pouring into the North Atlantic that made Europe get cold for 1,000 years. Well, then we should be a little bit concerned, because that's what's happening now. Right now, Greenland and the Arctic are melting. So there's a picture of how Greenland has been melting over the last 10 years. And down below, here's a picture of the Arctic melting away from 1979 to 2005. These are pictures during the summer when the ice is at its minimum. And you'll see that there's a significant amount of change there. In particular, now there's something called the Northwest Passage. You may have heard about it if you heard about old explorers who are trying to find some sneaky, quick route to get from Europe to the western United States by sailing north of Russia. Well, back when they were looking for the Northwest Passage, it didn't exist because it was snow-blocked or ice-blocked at all times of the year. But now it does exist, and now, in fact, oil companies are taking advantage of it to ship their oil during the summer months north of Russia. Of course, they helped create it. Maybe it's just all part of an elaborate business plan. I don't know. But this is a significant amount of melting if you think about it, especially if you have to imagine yourself thinking on the scale of thousands of years. The Ice Age ended 10,000 years ago. Now here we see in just 30 years the remaining bit of the polar ice cap is shrunk significantly. So people have noticed that there is a lot more fresh water going into the Atlantic. The salinity is going down, and some people are worried that it could trigger another younger Dryas event, but we don't really know. So we don't know if that's going to happen. But to get a better perspective on this kind of thing, we have to zoom out a lot further. Just looking at the last ice age really isn't nearly enough to tell what's going on. It's just like, just looking at the last night, you say, oh yes, there was a period of night, and ever since then it's been day. Well, that's sort of the attitude that people have. In fact, we have this silly geological timing system. This is a great book. This book is not silly. It's called The Holocene. The Holocene is a name for a geological period, though, which is the period after the last ice age. And that's sort of like having a name for the day, and then before that it was night or something like that. It's the geological periods get shrunk in a silly way when they get near to the point when we show up on the scene. Anyway, we have to zoom out to see what's going on. So 150 years ago, we have the Industrial Revolution and the start of this human-caused warming. 1,500 years ago, well, there were widespread empires. 15,000 years ago, that's around the tail end of the last ice age, as we've seen. So the younger Dryas kicked in around 13,000 years ago. But you need to zoom out a few more powers of 10 to really see what's going on. So you have to go out 150,000 years ago to get to the tail end of the previous ice age. So ice ages have been going on for a while, and they happen roughly, in a very irregular way, about every 100,000 years or so. So you really have to see a number of them before you can tell what's going on. The ice ages started, the serious ice ages started around 1.5 million years ago. So that means there's been about 10 ice ages since then. But the ice ages didn't start all of a sudden. There was a period of cooling, as we'll see, that's lasted for quite a bit longer than that. So if you got another power of 10, you get to 15 million years ago, and the cooling of the Earth's climate was well underway at that time. That's when apes just began to split off from other kinds of monkeys. And so we have to look at all these time scales, which you notice are significantly different powers of 10 here, to see what's going on with the climate. So let's zoom out a little bit and see what we see. So here's a bunch of graphs illustrating the climate at different time scales. So down at the bottom here is the last 150 years. So this is measured in kilo-annums, or thousands of years. So that's 150 years there, and so that's basically roughly since the Industrial Revolution, and you can see it's been warming up with lots of wiggles. And it's been warming up approximately a degree in that amount of time, as I said. But okay, that's way too small to see anything interesting, so let's zoom out by we're zooming out here by 2 powers of 10, and we jump up 2 powers of 10. So this is 16,000 years. So that's the end of the last ice age. Here's the younger Dryas, and here's this nice, wiggly, fairly constant weather we've been having ever since. And you can see it's warmed up about 5 degrees since the end of the last ice age. But we have to zoom out further. So, okay, let's zoom out to go back 150,000 years ago. Then you see that all this warming up that's been going on is this little thing here. And you see that in the last 150,000 years, basically what happened is we had an ice age, it got very cold, and then zoop, it warmed up. So the way this particular last ice age went was it warmed up suddenly, cooled down, and then warmed up suddenly. But that's just one of 10 ice ages, approximately 10 ice ages that's happened in the last million years. So, well, you can't really count ice ages, as you see here. Counting ice ages is counting the number of dents in this picture, but you have to decide how big they have to be to count. It's just a very complicated thing. So there's the last ice age, but you can see that there have been a bunch of them. And so that's what's been going on. But that's still a bit mysterious because it makes you wonder, well, how long has it been going on like that, and what happened before that? So let's zoom out a bit more. We really have to zoom out quite a bit more to see what's really going on. So here I'm zooming out to 65 million years ago. So the stuff I showed you before was just this period called rapid glacial cycles. Just this little bit here was what I was showing you before. 65 million years ago is a good time to start, because that's when the dinosaurs went extinct in a rather dramatic manner. And so this has been sort of the era of mammals. And you can see some interesting stuff has been going on in the last 65 million years. So basically, in a nutshell, it warmed up for a while and then cooled down quite a lot. It warmed up till around 55 million years ago. Interestingly, paleontologists talk about an optimum when it's as warm as possible. For some reason, they like it to be warm. So from their point of view, you'd think, oh, global warming, yay. So the optimum, so to speak, or maximum, I'd prefer to call it, happened 55 million years ago. It cooled down, and then, whoom, it took a big dive around 35 million years ago. That's when the Antarctic froze over. So through most of the history of the Earth, there haven't been ice caps. Around this time, there were crocodiles in Antarctica and palm trees and ferns. So the formation of the ice caps in the North and South Pole happened around then, and so that's a big, interesting puzzle. Why did it happen? We're used to it, but it's an unusual thing. It melted, the Antarctic melted for a while, and then it froze over again, and it's been getting colder ever since. But even more interesting in a way than the fact that it's getting colder is that the temperature variations have been getting bigger. You notice the curve gets really jittery near the edge here. So we're at a time period that's quite a bit colder than most of the history of the Earth, and also much more erratic. These wiggles happening about every 100,000 years ago, or so. Every 100,000 years or so. So the Holocene is probably that little black vertical line right at the edge of the graph, the so-called present. That's what they call it, the present, the nice period of time. Eventually, if humanity lives long ago, they'll say, well, back in the present, it's going to be a sort of embarrassing terminology. It's sort of like postmodernism. So anyway, the period of these big ice ages is called the Pleistocene. That's a skinny little period there. Then the Pliocene, then the Miocene, the Oligocene, Eocene, and Paleocene. I want to tell you a little bit about the history of this stretch of time, because it's, if you think about it on the grand scale of things, it's sort of the time period when things were more or less like they are now, in the sense that there were mammals and birds being the dominant life forms, whereas before things were very different. So this time period started out with a bang, quite literally. 65 million years ago, an asteroid that was 10 kilometers across, or 6 miles across, slammed into what's now the Yucatan Peninsula at an impact site called Chicxulub, which means tail of the devil. And that, as we'll see, is what probably killed off the dinosaurs. But there's some interesting other things to be seen in this map. You'll notice that Antarctica was not by itself. It was connected to Australia, and a lot of other features of the Earth were different. In particular, India had not yet slammed into Asia. And this probably has something to do with why the climate was so much warmer then, although it really is somewhat mysterious. So what happened? This is a really beautiful, idyllic scene here that was painted by someone at NASA. This looks like one of these new agey posters. But what it is one of the biggest disasters that's ever happened in the history of the Earth. It's a nice picture, though. So this enormous asteroid, 10 kilometers across, slammed into the Caribbean, into the sea, and millions of tons of rock were thrown up into the atmosphere. Lots of molten quartz shot around the whole world. People see little droplets of quartz that had been melted all around the world. It set wildfires all around the world. You can, if you go to my website, you can, if you're clever, you can get to some links that show the spread of the wildfires that people theorize happened at the time because of this molten quartz. And what that caused was a huge pall of smoke that wound up killing off the dinosaurs. Here's a picture of the actual impact. You can see it came in at a slant. They know the slant that it came in. It sent a huge tsunami, 50 to 100 meters tall, shooting over Texas. Unfortunately, way too early to do any good. Sorry for any Texans in the audience. I'm not talking about all of you. And the big effect of it was that it made the earth get dark for about a year. Plants basically were unable to photosynthesize completely for about a couple months, and so the dinosaurs died off. And that set the stage for us. Well, not quite us. So although I say things are more or less like we're familiar with, in the sense that birds and mammals were dominant, birds had the upper hand for a while there. So, in fact, it's true that the largest predators for several million years were these 8-foot-tall diatremas, or terror cranes. Here you see one eating a horse, which makes it look really huge until you remember that horses were this tall at the time. So it's not like Godzilla. It's just a pretty darn scary bird. But eventually, somehow, they died out, probably partially due to the cooling that occurred, and things became a bit more like the recognizable Earth we know. So 50 million years ago, after 15 million years of warming up, what happened was that Antarctica separated out from Australia, and also, shortly thereafter, not in this map, India hit Asia, forming the Himalayas and the huge Tibetan Plateau. And these things are two of the prime suspects for why the Earth got colder starting around then. For one, having Antarctica being separate from other land allows the ocean currents just to keep going round and round Antarctica, which means that it doesn't need to ever warm up. I mean, nothing's warming it up. Whereas when it was connected to other land masses, all the currents had to loop around, and so warm water would be hitting Antarctica, and people think that's why it was kept warm before, but not now. The Tibetan Plateau also has a huge impact on the climate. So the more snow you have around, the colder it gets, because snow is white and it reflects light. That's a basic instability in the climate system. When it gets cold, it gets white, and that makes it colder. When, conversely, we're seeing now that as snow is melting, large portions of the north are warming up even faster because dirt picks up a lot more heat than snow. And in fact, if you think about that, it makes you wonder what in the world is keeping things in balance. It's just the opposite of a feedback mechanism that keeps things stable. It's a feedback mechanism that makes things get thrown off. I could talk about that, but I guess I won't. But I will mention that there was a period before the Cambrian called the period of snowball Earth, when they believed the whole Earth was completely frozen over due to this kind of out of whack feedback. So it's actually sort of interesting what keeps things from going haywire. Anyway, what happened was that Antarctica froze over about 14 million years ago, and it cooled down everywhere. And then, at that time, serious ice ages started up. Here's a picture from around the middle of the last one. This is the coldest part of the last ice age, so you see that a lot more ice in Antarctica, glaciers covering a lot of Europe and North America. And since then, the ice has melted, and this is all happening in some tiny little sliver there. So if you think about it this way, you see that the Earth is really cold right now, and it's very unusually chilly. And so you might ask yourself, oh, gee, maybe a little global warming would be just the thing. And so that's a good question. I mean, I think it really needs to be addressed. So what is wrong with global warming, really? And the answer, though, is fairly simple. The answer is it's happening way too fast. It's happening shockingly fast. It's not being warm or being cold that kills off animals and plants. It's really the change in temperature. If the temperature changes faster than they're able to adapt to, that's the problem. And this is the scariest graph of all, as far as I'm concerned. This is a graph of carbon dioxide concentration in the Earth's atmosphere over the last few ice ages. The carbon dioxide really closely tracks the temperature. Unfortunately, I don't have both graphs here, the temperature and the carbon dioxide, but they really match. And so the last ice age was here, and then the ice age before that. And you can see that the amount of carbon dioxide during this whole period of ice ages has been oscillating in this band here until 1860, when it shot up almost vertically and is now about, well, it's significantly higher than any of this recent history. And that's because of the man-made carbon dioxide. And you really need to zoom in to this little last 1,000 years to begin to appreciate how it's shot up. It's really just shot up in the last 150 years. So what's happening is that we have this period of ice ages alternating with warm spells for quite a while, and then wham, right now, things are completely changing. It's a whole new ball game. So what's happening is that species of lots of animals and plants are trying to stay in the temperature zones that they're used to, and so the ones north of the equator are all moving north. They've done a survey of about 1,500 species, and they've found that on average, since 1950, they've been moving north 6 kilometers per decade, or about 10 miles per decade. So about a mile a year, animals are moving and plants are moving north. Of course, that's pretty tough for plants to move that fast, if you think about it. But well, you know, they die on one end of their habitat. They start to grow on the other end. But the real problem is they can't keep up, because since 1975, the actual temperature bands have been moving much faster than that. The temperature, that is, if you keep a line of equal temperature and see how it marches north as things warm up, they've been moving north at 4 kilometers per year, or about, I guess that means 6 miles a year. So there's no way that most animal and plant species can move that fast, especially, of course, you have to imagine that at the same time you have people with like cookie cutters ripping away their habitat all over the place, making it harder for them to move around. I don't know if anyone's even mentioned the idea of building a wall between us and Mexico and how that will affect the flow of animal life. I don't think they're planning to let animals through. And you see, this is just the beginning. So this is, I'm talking about now, but you see, we've seen this 1 degree warming since 1900, roughly, or about 0.8 degrees, but that's just the beginning. Here are all sorts of different people's projections for what's going to happen in the future, but you can see, even though the more conservative ones would be suggesting about 2 degrees more warming in the next century, or possibly quite a bit more, like 5. So what we've seen is climate moving along, and then, whoom, something happening much faster than life forms can adapt to. That's the problem with global warming, from the point of view of the ecosystem, as opposed to just people. So it seems quite likely that we're entering a whole new geological era. And in fact, people have given a name to it, the Anthropocene. That is, it's quite possible that the ice ages are done with now, and that we're entering a new period of extreme warming. And as with other changes from one geological period to another, we'll probably see a lot of extinction. So in fact, just around now, in the last few years, we passed the temperature record that was set 120,000 years ago. So I don't know if we should have a party, so the last time it's been this warm was before the end of the last ice age. And if we just warm up 1 more degree, which will probably happen in another 50 years, the Earth will be the hottest it's been in 1.35 million years. That's when the ice ages began. So in 2050, we'll be out of the ice ages and into some completely new territory, so to speak. And people have done a lot of different projections on what that's going to mean for animals and plants, and they estimate something like between 15 to 40% of all species are going to get killed off. And that's due to the warming. Of course, there's also lots of other things going on. So for example, as you know, lots of things are going on. 90% of large fishes have been killed off in the ocean over the last 100 years. We're seeing major die-off in bird species in America. And we're seeing a lot of amphibian species going extinct, about 150 in the last 50 years. All sorts of different things for all sorts of different reasons, and this global warming is just one part of the whole story. So to understand what this really means for the world, we have to go back even further in time and look at what are called the mass extinction events. That is, the times when significant fractions of the species on the planet of the Earth have been wiped out. So I've just mentioned one of those, the end of the dinosaurs, but there are others. And here's a picture of them. So here's a graph where the present is over on the left-hand side, so time is going this way. And it's a graph of extinctions. These blue spikes are the mass extinction events. It's telling you what percent, not of species went extinct, but of genera went extinct. So genera is the plural of genus. So we're Homo sapiens, so sapiens is our species, and then Homo is the genus. So there's also like Homo neanderthalensis, Homo australopithecus, all those different variants of genus Homo form one genus, and that's what's being counted here. So the idea is that if just a species goes extinct, there will be some other species that are pretty similar that could then later on adapt and branch out to fill any niche that was left. But if a genus is gone, that's more significant. So at the end of the age of the dinosaurs, 30% of genera went extinct. At the end of the Eocene, that's when the temperature suddenly dropped. I'll just zip back there for you. So here, that was a major extinction event. And you can see that this particular one is probably due to the drastic cooling. I'm not saying that all extinction events are due to temperature change, of course, that the end of the dinosaurs was something completely different, but that one's probably due to the sudden cooling. And so that end of the Eocene extinction event was the biggest one since the end of the dinosaurs. So 10% of genera went extinct. And the current one is not plotted on here on purpose because it's underway. We don't know what's going to happen. The real big one was at the end of the Permian. The Permian-Triassic extinction was the biggest of all, as far as we can tell. As you can see here, about 50 or 45 or 50% of genera went extinct. There's a book that's available out in the lobby called When the Earth Nearly Died, I think, something like that, which is about that. And no one's quite sure why it happened, but one possibility is that it's known there are huge amounts of volcanic eruptions then. There was some kind of, major tectonic event, And it's possible that there was a huge burst of global warming due to the release of a lot of carbon dioxide from volcanoes. But there are other competing theories for that. And you can see that there were other major ones earlier on. This yellow curve is sort of interesting. That's a sort of averaged out curve of extinctions. And you can see that on average, the severity of extinctions has been going down, which may actually mean that this idea of survival of the fittest or of evolution as a kind of advance has something to it. It may be that life is just getting better at adapting to changes overall. Let's see. So what's going to stop things? Well, luckily, we'll run out of oil. Yay. So different people predict that will happen at different times. Don't worry, I'm not running for office. So here are lots of different projections. You see that most of them predict a peak oil usage sometime around 2025 or so. This is in millions of barrels a day. So right now, or when this chart was compiled, it's 85 million barrels of oil burnt a day. It may go up to about 120 or so, and it'll start going back down. Just so you get a sense of how much agreement there is on this, that red curve there is prepared by Exxon, whereas the green curve there is prepared by British Petroleum, which is, I guess green is the right color for them. They're, as oil companies go, they're green. But the point is that for the point of view of human politics, it may make a huge, big difference whether the oil more or less runs out around 2075 or 2125. But from the point of view of the Earth as a whole, it's not that big a deal. I guess it may affect how many species are killed off. But the point is, it's going to end pretty soon. And so you could take heart from this and say, well, you know, we're going to be miserable, of course, but at least this rise in the carbon dioxide concentration of the Earth's atmosphere is going to stop fairly soon, and then hopefully it will level off in times that we don't completely send the climate totally out of whack from what we're used to. But that's an open question. So the question is, what can we burn next? There's a lot of stuff to burn. So there are 3 trillion barrels of oil left to burn. There's just 1 trillion barrels of natural gas equivalent. These are converted to be the equivalent amount of energy. So there's less natural gas. There's a bit more coal, 4.5 trillion barrels worth of coal. There's about the same amount of tar sands, 4.3 trillion barrels. Tar sands is this goopy, tarry stuff that with a lot of work you can extract the oil. But dwarfing all of those utterly are 72,000 trillion barrels of stuff called methane hydrates. So I'm sure you all hear about methane hydrates. No, you never hear about methane hydrates. What are methane hydrates? Well, in the ocean, in the northern latitudes, on the sea floor, there's this weird stuff that's a mixture of ice and methane. It's ice molecules that have little methane molecules fit into the empty space. As you know, ice is lighter than water. It's a very loose arrangement of water molecules, and there's enough room to pop a methane in there, and you get this funny mix called methane hydrate. If you dig up a piece of that and bring it up to the up into the air, it's unstable, and the methane goes and fizzes out. Apparently, you can see on the web some movies of what it actually looks like. But there's a bunch of that stuff down there, and of course, people are scheming for how to dig it up and burn it. And that is precisely what you should do if you want to, first of all, keep the carbon burning economy going, and second of all, if you want to make global warming that's approximately 10,000 times worse than what we see now. Methane hydrates are pretty interesting because there's so much of them and they're sort of mysterious. They're are times when they have impacted the climate, and I should just point out one. I should go back a bit. So see, what we're facing now is this funny thing of a sudden spike of temperature, very rapid spike of temperature. And so it's interesting to look around for other comparable events and see what happens to the world when there are these spikes. So if you look at this graph, you look at this thing here, blip, see that little thing? That's called the Paleocene-Eocene Thermal Maximum, or PETM. It's not the biggest change in temperature, but it's a very sudden change in temperature of about 2 degrees that lasted for just about 1,000 years, and it was a warming spike, and people wonder what caused it. And what they think caused it was a methane burp. A methane burp, in case, excuse me, a methane burp is when the methane hydrates on the ocean floor somehow get destabilized and emit all this methane that's down there. Now, methane's an even more of a greenhouse gas than carbon dioxide, which is why, in fact, people are seriously concerned about farting cows. I'm serious. Farting cows are a substantial contributor to global warming. But this massive release of methane from methane hydrates was even more important by far. And they noticed that there was significant extinctions at the time. I guess 30% of foraminifera died out at the time. Foraminifera, or forams, are little critters float around in the sea that have a calcium shell that eventually turn into limestone when they die and fall to the bottom. So when you look at limestone, that's largely foraminifera and other things like diatoms. So what it meant was that there was a sudden change in water temperatures during that period that killed off lots of those guys. There have been probably other extinctions that were caused by massive release of methane, and that's the alternate theory for that big die-off I mentioned the extinction at the end of the Permian. It's known that there was a huge burst in warming, so the two competing theories are that carbon dioxide from volcanoes or methane from a methane burp is responsible, and people are arguing about it now. Anyway, if you want to be really paranoid, you can make up scenarios where people digging for methane hydrates causes a methane burp. I don't know how likely that is, but if that doesn't happen, well, maybe we'll just burn it and turn it into carbon dioxide, and we'll have more or less the same effect. So the question really is, can we resist trying to keep going our normal course of burning and try to switch over to some other sources of energy? And of course, there are large industries devoted to keeping business as usual. I just like this instance here. So here's a note placed by Philip Cooney, who is the chief of staff of the White House Council on Environmental Quality in 2002. This is a scientific report that came to his desk about global warming that was prepared by various environmental agencies. And here he is watering it down, saying, instead of the Earth is undergoing a period of relatively rapid change, changes it to the Earth may be undergoing a period of relatively rapid change. And so this is an example of how various political forces are pushing us away from realizing the significance of what's going on. When these notes were discovered, Philip Cooney suddenly decided he needed to spend more time with his family, which apparently was Exxon. He said he wanted to see his family, and I guess he saw him for a while, but then he went to work for Exxon. So in fact, as you know, Exxon has a major role in setting up this network of think tanks that try to downplay the importance of global warming. And so the question is, can we sort of see through the baloney to see what's really going on in time to have any effect? It may well be already too late really to have any effect. So we have to contemplate the possibility of a mass extinction. In the long run, you don't have to worry too much about mass extinctions, where by the long run now I mean maybe periods of, say, 10 million years or so. So a mass extinction event is a pretty sad thing. Here's a picture of the seafloor before the biggest mass extinction event and afterwards. You can see the complete impoverishment of of biodiversity that happened then. But then, after tens of millions of years, it bounced back and it became even more interesting. So life does have this amazing way of bouncing back from these major disasters, and it even seems to get more interesting each time. So from that point of view, which is a very sort of cosmic, or at least long-term terrestrial perspective, we don't really need to worry. We may die out, but it's very unlikely that we're going to kill off all life on Earth. And even if we do, really, there's nothing to worry about. There's lots more where that came from. There are about 100 billion stars in this galaxy. If one of them just manages to have life for a while and it fizzles out, well, I'm sure there's plenty of interesting stuff happening elsewhere. Since I tend to think on large scales, that's usually how I sort of calm myself down after reading the newspapers. You know, so something happened over there. I'm actually usually more interested in what's happening over there. There's a very large black hole there. That's sort of more interesting to me. And really, that galaxy isn't such a big deal. There are 10 billion of them in the observable universe. The observable universe means not just what we can see now, but what we could ever see. In other words, if you look back into time to the Big Bang, you see 10 billion galaxies. So that means that there are about 10 to the 21 stars in the universe, of which ours is just one. So on the grand scale of things, it doesn't really matter to anyone what happens, except, well, for us, of course. So we're sort of on our own here, I think. And the question is, can we zoom out in time? Thanks.
Thank you, John.
Sure.
We should ask you to give a lecture on physics.
Yeah, that's what I know something about. I would have liked to have talked about math and physics, but I thought I should talk about something that might have some, be some good, do some good.
Well, what I love actually is that you're not only sideways in time, you're sideways, for me, to a lot of the kind of general story about global warming that's going on right now. We're all, Al Gore explains about the Gulf Stream and how that's going to cause the end of Europe if it shuts off because of the water in the North Atlantic. And you're saying, well, yeah, that's one of the theories. And so we're looking not only at, I realize, unstable climate regime, just looking at the climate issue here, and probably lots of other major issues that we look at have this kind of quality when you back off from them. But there's also instability in the understanding. And so we're always, in a sense, dealing with a range of what might actually be going on. And this is part of what is really, really tough for policymakers who are in a political framework, in a democracy, to say, well, we're not dead sure on this, but we're trying to reduce risk, and so they overposition themselves. And what one would like to see is more of this comfort with uncertainty that you put out in this talk introduced into the whole political process. And that's what I especially love about what you've done here. We're just now collecting questions. While we're dealing with a few written ones here and Kevin's sorting, why don't we have a hand raise or two? Somebody who's got a question, you just want to yell right out, right here.
Yes.
Is Stewart right that there's actually a critique of the theory that the slowing or stopping of the Gulf Stream would cool Europe? Or was your point only that it may not have been the cause of the younger Dryas?
The question was, which I'll give for the television cameras, what is the actual doubt that is currently being raised about the Gulf Stream theory of the cooling of Europe?
So about what will happen, I think there's a huge amount of uncertainty. So most of the research is about what did happen and what is happening. And so this book is actually pretty interesting by Mark Bowen. I guess it's on sale out there. It's called Thin Ice, and it's about people it's about the history of the study of climate change, focusing on people who are digging ice cores around the tropics. And it shows there's a lot of controversy about the cause of this younger Dryas episode, where first a bunch of people thought that what's going on in the Atlantic was really the central determinant of that younger Dryas episode, but then people started thinking that the Pacific Ocean is much more significant, partially just because it's so much bigger in determining global climate. And so, from the point of view of this book, that idea of the turning off of the Gulf Stream being the cause of the younger Dryas is an old-fashioned theory. I'm sure it's still being debated, and I'm not up on the latest thing. That's one thing.
But that doesn't affect the prediction that the stopping of the Gulf Stream now would affect Europe and cooling.
It does affect it, because I think the only way we could predict those kind of things is by comparing them to previous events. In other words, no one is good enough to build up a model of the Atlantic that you can press a button on your computer and see what will happen. So they have to rely on this historical evidence. And I just changed one of my transparencies a couple days ago, where I had said that the Gulf Stream was what kept Europe warm. So a couple days ago I said, the Gulf Stream warms Europe. And then a climate scientist friend of mine emailed me saying, no, we've just discovered that that's not mainly it. It's something much more complicated. So that would also have a huge impact on these questions. So I'm unfortunately not an expert on this. I'll have to do some reading myself.
One of the things that I've seen as a result of this discussion about climate change and realizing how ferociously important it is the science is getting better and better, the data collection is getting better and better, the theories are probably getting better, the models are getting better, and that's the stuff that you want to have go ahead, because then you get more convergence. Michael Berlinger here, where are you? Back there. Says, how has this perspective affected your lifestyle? Or what is the moral impact of all this?
I feel guilty when I fly around giving talks on global warming, because I'm using a lot of fuel flying around. This is the first talk I've given on this subject, but I try to burn as little carbon as I can. I guess more than that, just for me, I find myself trying to learn to live with lots of different temporal perspectives simultaneously. So I spend a lot of time studying the real long term. I could have given a lot of very fun talk about what's going to be the big problem in the future, namely all the stars burning out and the universe expanding to the point where each atom is completely isolated from every other atom. To me, that's a pretty interesting problem. I just figured you might have a little trouble getting too concerned about that. But when you think about these things on these widely varying time scales, you really do need to somehow come to terms with the fact that something can be fine on one time scale and terrible on another time scale, and then fine on an even smaller time scale and terrible on an even smaller time scale, and they all coexist. And I can't really say what the impact has been, but it somehow made me think about things differently.
Here's a question without a name. Why do species have trouble adapting to a few degrees of variation in temperature? Humans seem to adapt to a range of 10 or 20 degrees even before technology.
That's a good question. I think humans had technology for quite a while. A fur coat and a fire and a cave makes quite a difference if you've ever been out in an ice age. I don't really know why the animals have more trouble adapting than us, apart from the fact that we have technology. I think so I don't really know. One thing that's very interesting to me, though, is that we're seeing now a strong selection for species of certain sorts. So I don't think anyone's worried about rats and pigeons, for example. They're going to do fine. Cockroaches, great. So what I think we're going to see is, because not just the problem of global warming, but the bigger problem in a sense of loss of habitat, is that the species that will survive are the ones that live well in close proximity to humans. And so those will be mainly pests, pets, diseases, cute animals in zoos, and animals that we eat. So in fact, if you wanted to keep rhinoceri from going extinct, you should probably start eating them, actually. But not just by shooting them, but not by shooting them out in the wild, of course, but by farming them. So again, I don't really know the full answer to your question, but it is going to become a very important issue to see what survives and what doesn't, and why.
That's a wonderful, that'll be one of the definitions of the Anthropocene, presumably, for the future geologists, is they'll find these species, all of which have the characteristic of being like raccoons.
That's right. Coyotes have moved into Los Angeles. There was one that was found in Central Park recently. Sorry, my sound is flickering on and off, I think. And they're also around Washington, D.C., where my folks live. And hopefully they'll get some wolves in there to eat all the deer that are eating all the plants.
Okay, Gary Wolf has a question. Where are you, Gary? Right here. And I'm going to broaden the question. He says, can we cool the Earth down by painting it white, please? And this raises the whole issue of what are called amelioration schemes. There's some of them in Jim Lovelock's wonderful book, The Revenge of Gaia, which just came out in the US. And there's some folks over here at Lawrence Livermore Labs who've been looking at some of the kind of, what if you, while you're waiting for the run out of oil and deciding not to do the clathrates, the methyl hydrates and so on, what do you do to keep things in hand for a while? And one of the suggestions is paint the Earth white. Certainly you can paint roofs white, and it would be sensible to do that anyway. Highways white, it'd be interesting, actually.
Right, I was just going to, oh, you stole my suggestion, which is don't use black asphalt. It's actually not that terribly hard to make highways be white. This isn't going to be enough, but it's something that's pretty doable.
Yeah, that'd be fun to do, actually.
Cool
some county could just say, okay, the deal, you live in this county, you have a white roof, and we drive on white streets. See how
yeah, they're
that plays
trying
out.
to make the roofs in Los Angeles white.
Really?
Yeah, they have an
That's finally
initiative.
happening.
Yeah.
For years, people wanted to paint the roofs white, and the neighbors said, no, it's too bright, and they had rules against painting your roof white. Anyway, other amelioration things, one of them is to go out to Al Gore's favorite point, which is the Lagrange 1 point, it's the gravitationally stable point between here and the sun, where, among other things, it would be swell to have a camera getting a real-time photo of the Earth with the sun behind it. So it's the full disk of the Earth with turning and having weather and also giving temperature readings, which you would like to have. But it would also be possible to, and this is one of the things that Jim Lovelock mentioned, to basically have something which, right at that point, expands out and cuts off some of the light coming from the sun into the Earth. And a disk of very light material, 7 miles in diameter, which would be relatively easy to spin out, put there and spin out, could cut the amount of sunlight reaching the Earth enough to head off some of the warming that we're having.
Really, just 7 miles would be enough to do something?
That's
surprising.
I'm waving my hands real fast here.
Okay.
I don't know the numbers.
Because that's so small.
Yeah, anyway, I mentioned this to Al Gore a couple of weeks ago, and he went batshit. He basically said, oh, that's a real good experiment to run. Let's just see if we can, change the whole Earth at once. And he was not in favor of doing that. But you can imagine things getting desperate enough to where, by some international agreement, because obviously it would take that, but like the kind of agreement we had about Antarctica being the continent for science and so on, okay, let's put something there, move it out a little bit, see if it helps. If it helps, move it out a little bit more. Back off if it's less, because you could control it from there. Does this kind of thing appeal to you at all?
I don't think anything appeals to me about global warming. so I mean, there will, yeah, you run a big risk, of course, when you start messing with things even further. So, but we run a huge risk not messing with things further. So I think instead of me saying what I think I would like, I think I just spend most of my time trying to figure out what people are likely to do. So if somehow the global warming becomes a very noticeable issue, people will start pushing for these technological solutions. Mm-hmm. And I think that will just be in line with what's been going on ever since technology began, namely that we acquire more and more control over our environment, and eventually I think we're sort of headed that way. The Earth is going to be our baby to take care of as well as we can. That's the idea of the Anthropocene. Mm-hmm. And whether a particular measure winds up helping or ruining things, you know, it can be very hard to tell.
Yeah, well, in line with the Anthropocene, we had a talk from Rusty Schweikert several years ago in this series on the what he referred to as the asteroid threat over the next 100,000 years. The 165 million years ago, that kind of thing could happen again any time, except that now humans are in position to be able to detect ones that are on a collision course, go out there and actually divert them. It doesn't take a whole lot of energy or time to divert an incoming asteroid if you have a couple of years advance warning. Well, among other things, this just completely throws off the whole past, because in the past we've had these big asteroids coming in from time to time and bashing the Earth.
That's right.
And in the Anthropocene, that doesn't happen anymore.
If we get our act together, that's what we won't have to worry about asteroids too much. Yeah, an interesting thing is that there's a lot of argument about how many major extinctions were caused by large rocks hitting the Earth. There's pretty good evidence for the end of the dinosaurs. I mean, there's a crater there that happened at the right time. There's still, though, a lot of controversy about whether that was really the thing that did them in. There's some people who say, hey, look, we can see they're dying out even before that. For all the earlier extinctions, it's much more mysterious. There are sort of different camps. There's some people that think that asteroids are a major cause of these mass extinction events. So, and one of the cuter theories along those lines is that these asteroid impacts happen more or less regularly whenever the sun goes through the plane of the galaxy, because that perturbs asteroids. And if that's true, then we can expect the next one in 10 million years. So there could be another big one to worry about in 10 million years, but we should have lots to worry about before that happens.
Other stuff before then.
Yeah.
Okay, here's a question from Will Hurst. Where are you, Will? Will, by the way, is the founding sponsor of this series, which thank you for that. And for this question, how accurate are any computer models of climate? Since we can't predict weather more than a week ahead, isn't this all basically pretty profoundly chaotic?
Well, a lot of chaotic wiggles average out in the medium term. So I think we're getting pretty decent at predicting climate over a period of the next 100 years. We're terrible at predicting it for longer periods than that. So these big changes that I was showing on my big graph, like the Eocene warming up and then cooling down, we really have very little clue about those kind of things. People have pretty good models, actually, for what causes the ice ages. It's basically just due to variations in the Earth's orbit. So again, it depends a lot on the time scales you're talking about, and of course, for political purposes, it's the next 100 years is what you care about a lot. And I think it's just pretty clear to me that we're headed for warming for the next 100 years. You just need to look at that graph of carbon dioxide concentration, and I think that sort of says it. Whether it's going to be just 1 degree or 5 degrees, well, then you have to start arguing about your climate models. And I'm not an expert in climate models either, so. I can't really say.
Well, exactly. I love that you say that the political perspective makes you look at the next 100 years. If only the next 100 years were strong in the political perspective. In fact, one of the things that
our grandchildren.
I mentioned Gore somewhat deprecatingly, but I don't mean it, because he's said he wants to do one of these talks in the series, and the subject would be how basically long-term thinking and long-term responsibility can be reintroduced into the whole political electoral process. Because right now we tend to be focusing on the next election, which is not in 100 years.
No.
And the results of it don't last for 100 years. Here's a question from Phil Cass. Where are you? Somewhere here. So, he says, that's an awful lot of methane hydrate.
Yes.
But isn't it already sublimating? Isn't it likely to end up in the atmosphere before we get a chance to burn it? I mean, the oceans are getting warmer. Are they going to cause a burp?
Well, I suppose warming oceans could cause a methane burp, and I guess that would be a kind of thing where you really need to look back at the geological record. And I guess the big problem there is that it's very hard to tell whether warming oceans caused a methane burp or whether a methane burp caused warming oceans. That's the problem with a lot of these geological things. You see, hey, look, there's a lot of methane and the oceans are warm, but you need to know things on a very fine scale to know which caused which. I haven't heard of any evidence that methane is sublimating out yet.
Well, there's another question. What is the origin of the methane hydrates? Is there a biological origin for them? Or
I'm sorry, I don't know that either. It must be biological because the carbon cycle is largely run by biological entities, and I'm sorry, I don't know how it all got down there. It's terrible, I should know, but I don't.
I've seen a picture, by the way, you were mentioning there are things on the web. If you look up methane hydrates or clathrates, they're also called, you'll see pictures of a person holding this white chunk of, obviously, ice in their hand with flames coming out of it. And
yeah, you can just take a hunk of this stuff, hold a match over it, and it'll burn. Because of the methane coming out.
There's an image of the Earth. Enzo Z asks, plotted against the Earth's polarity reversals, is there a causal relationship between Earth's fluctuations of temperature and Earth's polarity? And while we're at it, how about the orbit of the Milky Way around the galactic core every, 26, he has 1,000, that's not right.
26 million years?
26 million years. Any relationship there?
So by polarity, I guess he or she means the
magnetic polarity. I think.
The magnetic field of the Earth flips erratically. I don't think there's any correlation between that and climate. Right when it's happening, there's not much of a magnetic field, and so there's be a lot more cosmic rays hitting ground. That would be pretty scary. I don't really know if people have noticed extinctions due to that, but I have never heard of any extinctions being due to that. About the sun and Earth going around the galaxy, that is this theory that I just mentioned a little while ago, that periodically we're not going around perfectly in plane with the rest of the galaxy. So twice around we go through more thick stuff that shakes us loose some comets and asteroids from their usual orbits, and then they might be more likely to smack into us. So people have done a lot of studies where they look at big old craters and plot the frequency of their occurrence with this so-called galactic year, and they seem to see that there is some kind of matchup there. So, as I said, that means we have to worry in 10 million years from now. But
notice on your website you always have interesting material of whatever current images and data coming from Mars is. What's your interest in Mars?
Part of it is just that it looks cool, and it's nice. It's nice to have some other planets to look at. Part of, I guess, another point. If I guess make a political point while I'm at it, the idea of sending people to Mars is really ridiculous, and they're planning to spend billions and billions of dollars sending people to Mars. So part of my point is that by sending these machines to Mars, you can see everything that you would see anyway. To my mind, manned space travel is a bit like putting a goldfish on Mount Everest. You know, you say, well, we did it. Yeah, and a goldfish has experienced what it's like to be on Mount Everest. But it's not really all that, it's not really worth it.
On that note, thank you very much, John Baez.
Thanks.